right. Okay, so here we are on Monday. This is technically our second lecture, and I will start with this little reminder of where we are at. Last time we just introduced the syllabus and we went through any kind of just a little bit of review about evolution and speciation. Again, like I will be doing today, sharing kind of misconceptions that I had as I got into some of these topics. And you know, we get to zoom out in this second half of the class. I kind of put this little pyramid on the board last time where we kind of zoom out into populations and communities and ecosystems. And one of the things that we're going to do today is really talk about the Earth, and we're going to talk about the biomes, the different ecosystems and communities that we find in those ecosystems, just to kind of, again, give us a good base layer before we get into the rest of the information for the class. This is a science majors class, right? So everybody in here is interested in one of these aspects of science, but it might not necessarily just be biology. This might be something that you have to take. So one of the things, or you might not take many more science classes after this. I don't really know how it's going to go. So today, really, what I want to do to try and make some of the things that we talk about on Wednesday make a little bit more sense. You know, we will start Wednesday's lecture talking about the formation of the Earth and what happens as the Earth starts to cool and the continents form and start to move around and organisms, evolve in the ocean and then move out onto land. We'll talk about this Earth history starting at about 4.6 billion years ago, right? And if you're like me, you may wonder, well, what was going around before? How far back can we go? And so today, what we're going to do is we're going to talk a little bit about this, what I have put on D2L and called the Earth Science PowerPoint, in which I've tried to condense a little information about the entire fields of astronomy, climatology, and geology, just to give us a little sense about how these different biomes are created, right? That's where we're going. And it should set the stage for the Earth history stuff that we talk about on Wednesday. Rather than just throwing some random dates out there, I thought maybe we could spend today talking a little bit about the science. How do we know these things? If you haven't gotten to take some of these classes before. Again, I remember me being in like a junior or senior in high school, not having anybody but coaches to talk to that didn't want to talk about this type of stuff. So even though this is not an astronomy class or a climatology class or a geology class, we're going to skim the surface of those things today. And I invite in, what I'm trying to preface here is that quiz information and exam one information is really going to start here with Earth history stuff. So the things that we talk about today are broad and are not really going to show up on the quiz or the exam. But I think it's important to get a good foundation to understand, how do we know some of these things getting into the discussion into the rest of the semester. So don't worry about having to take a bunch of detailed notes. Feel free to get into some of the conversations, ask questions. I will try and again address some of the misconceptions that I had going through some of these topics beyond the scope of just this biology class. And just a heads up, we're going to get into explaining some of the geology of Texas, but let's go back a little further than that. This was a picture that we saw, I think it was the last one that we ended with in our lecture on whatever day that was. Wednesday? That was last Wednesday? Seems like a while back. And I said this was kind of a famous image because it was the deep Hubble image that was taken like back in the 1980s when they didn't think they were actually going to see anything. They pointed that powerful Hubble telescope at a pocket of sky that they thought was completely blank. And to give you an idea of the field of view that this telescope captures, if you stick your arm out as far as you can stick it, it's about 1/10 of the width of your pinky, right? So a sliver of your pinky at arm distance is about how much of the sky this captures. And again, when they pointed it into a blank pocket of space, they thought they weren't going to see anything, but they came back with all of the galaxies that we see here. And I said last time, from this image, they were able to gauge something about galactic evolution, because you can zoom over here to see two galaxies that are about to collide, right? And then you could zoom over here and see two galaxies that have just collided. You can see them at different stages of collision, and you can see some of them that aren't colliding at all. So there was, it was obviously one big discovery to find out that we are not the only galaxy out there, that there's trillions of other galaxies out there. And this is a good example of how for every one thing that you learn in science, it kind of raises 10 more questions, right? So there was a bunch of questions like, okay, all right, there's other galaxies out there, but are they static? Are they just kind of floating and hovering at equal distance from one another? Or are they all coming together? Are they all flying apart? Like, what's going on? Some of them are colliding, right? And as they continue to make measurements, and this is something that in the 20 years from when I was sitting in this class to now, they figured out that this whole cluster, like the clump of galaxies as a whole, is not only continuing to expand, but it is accelerating as it expands. And, you know, we can draw a couple of things from that. That's one of the reasons they can deduce something about the Big Bang, that if we go back in time, that all of these galaxies were closer together. And let me say something about that real quick, just to address misconceptions, again, that I had. I thought, you know, because I'm from a small town where I used to go out at night, and when they had firecrackers, I would like to do those bottle rockets and throw them up in the air, and they would go up there and explode, right? And you could see from a single point of explosion, all of the pieces of the bottle rocket go off in different directions. And so I thought, you know, that the Big Bang was something like that if we could trace it back in time, we could find some point of expansion. And that would tell us, you know, kind of where this expansion came from. But that's not exactly how it goes. Like you hear that the expansion of the universe, of this whole cluster of galaxies, is expanding everywhere at once, right? That's weird to say. Instead of in the middle of the room, a bomb going off, right? And shrapnel hitting all of the walls. The expansion doesn't happen like that. It happens in a weird way where if I'm standing right here in this point in the universe and I look out at the distant galaxies, it can be the case that I'll say it this way. I'm about to say that a relatively close galaxy to me, the close clusters of galaxies, some of them are condensing and clustering into these super galaxies. But distant galaxies, ones that are not very close together, that have these void pockets of space between them, those are getting further apart. Because, you know, another misconception about this expansion, I'm about to talk about how it expands, but another misconception about this what is expanding in the first place are these void pockets of empty space. The galaxies themselves are not expanding. You and I, as we sit here, are not expanding, right? But if you could imagine this cluster of galaxies like a bathtub of bubbles, like a Mr. Bubble bath that we just poured. In that bubble bath, right, in the middle of those bubbles, you've got these little void pockets of empty space. And it's those little pockets of empty space in the middle of those bubbles that are doing the expansion, right? The little bubble, the soapy film that is the bubble, that's the stuff that's you and me in the galaxies. And those can be clustered together and can merge where you've got these void pockets of space. And it's those void pockets of space that are expanding, not the actual galaxies. Now here's the effect. Here's what's weird about what I was just about to say, that from our perspective, where we are at in the universe now, when we look out, we can see these distant galaxies all expanding away from us in all directions. But if we could somehow move from where we are in the universe to a completely different part of the universe over here and look out, we would also see things expanding away from us in all directions, right? It's not just like a bomb going off in the middle of the room. Instead, think of it this way. This was maybe the best way I've heard it explained from a guy out at the McDonald Observatory out in West Texas. That's not the Ronald McDonald Observatory, but the UT Science Observatory out there. And the way to think of this expansion of the universe is, it would be as if we filled this room full of tennis balls, right? All the way to the ceiling. We couldn't fit any more tennis balls in here. Now, you know, we're stuck in the middle of some of these tennis balls, right? Ethan, we've got like 10 tennis balls between us right now. What happens, like imagine if each of those tennis balls started to swell and expand. It would quickly, you know, blow the walls and the ceiling off of this room, and we would be expand, not us, but the space, the tennis balls themselves would be expanding. And what it would do, right, Ethan and I, we've got 10 tennis balls between us, and each of those tennis balls are expanding at a fixed rate, so you and I are getting further apart, right? But Isabella, we've got like 20 tennis balls between us. So you and I are actually getting pushed further apart at a faster rate because there's more tennis balls between us doing the expansion, right? And Alexa, there's so many tennis balls between you and I that, obviously we're getting pushed further apart from one another at an even faster rate than anybody else. What's interesting about the light coming to us from these distant galaxies, again, I'm not intending to get this deep into an astronomy PowerPoint, but if I were to click the light on right now, light would fill this room almost in an instant. But if we think about the vast distances of space, it takes some time for light to move through that space. And to give you a reference, like if the sun were to stop shining right now, we wouldn't know it for about 7 seconds. It takes about 7 seconds for the light of the sun to go from the surface of the sun to us here on Earth. And I say that because, if we think about light moving through space, we're seeing light as it was when it left, like ancient light. And there's a consequence of this expansion of the galaxy that there is a limit to the observable universe, right? If there's so many tennis balls between Alexa and I that the light from my galaxy is coming towards you and the light from your galaxy is coming my direction. But since there's so many tennis balls between us expanding, that light is going to continue to move towards each other but never reach one another. So depending on where we are in the universe, there's a limit to our observable edge to the universe. That doesn't mean that there's not clusters of galaxies past that, right? There's just a limit to where we can stop our perception. Okay, anyway, let's move on. This Hubble constant, right, this expansion of the galaxies was one of the things that the Hubble telescope was trying to measure. And it is with this measurement of how fast those tennis balls are expanding, that's how we can calculate the age of the universe. And it has been calculated with ever more accuracy, increasing accuracy. It's somewhere around 13.872, if we're going to be careful, billion years ago was the start of the universe. And again, they're getting this by figuring out how fast the universe is expanding and running that back in the past. And it leads to some consequences, right? Some predictions. It's interesting that this has only been known for less than 100 years. That is wild. And it has led to this graph. Let me explain what's going on here. Again, this is not going to be on the exam, but it's interesting to think about that there's no periodic table of elements in here, but if we go back and reverse play this expansion of the universe. So instead, all the galaxies are getting crunched into a tighter, smaller point in space. What we know about things that get pushed and put into smaller volume, like the temperature goes up. Like I had this discussion with somebody earlier in the class, and they were talking about it. If you were to compress water, would it heat up? And I said, yeah, that's how your car works. You put a little bit of liquid fuel into one of those chambers, and again, I'm not a mechanic, so there's probably better terms for that, and then that piston just pushes down and compresses that gas, and it compresses it so much that the heat goes to a certain point where ignition happens, and then that gas kind of turns into a flame, and it kind of causes a little explosion, and that pushes the piston back up, and as that piston is pushed up, it's connected to an arm that pushes another piston down. And that downward force of another piston is what kind of compresses a little pocket of gas to the point where it ignites, and then that piston pushes back up. So in your car, you've got these multiple pistons that are constantly pushing things, little pockets of fuel up and down to reach an ignition point. And if we go back in time, that's kind of what's happening. All these galaxies are getting crushed into a smaller point in space. And this line represents a point when things were so hot and so dense that electrons and protons were bouncing around so fast that electrons couldn't even settle into orbit around protons, right? Those subatomic particles and forces that hold protons and neutrons together weren't strong enough to hold them together, so you didn't have any kind of physical particles at all. It was just heat, just radiation. So this is kind of the line where there was just a ball of energy and ball of heat. Now, we could think of, you know, where did that ball of energy, where did that ball of heat come from? Is there some type of rebounding universe? It doesn't say anything about whether or not this universe that we're in is the only one, or whether or not there are multiple ones out there. So there's actually multiple experiments that they're trying to come up with now to test to see if there is any kind of evidence for multiverse and things like that. Well beyond the scope of this class, but I just want you to see, you know, how we get this idea of our Big Bang, and I don't know, just to give you an idea of astronomy, I guess. Obviously, this is well beyond the scope of our class, but I guess where I'm really going with this is we're going to start throwing around years like the age of the Earth, the age of the universe, the age of several different things, and it's worth kind of giving us a reference point to the age of the universe as far back as we can possibly go with science at its current point. Now, this graph, this first one was done like back in the late 90s, and this was done like in 2004. So you can see the resolution of the image has gotten better. But what this is an image of is the expansion of that initial heat. Just to go back to this slide, this is showing us as we go back in time, all of the physical matter, the galaxies were clustered so tightly together, they were so hot that there wasn't actually physical matter, it was all just a ball of energy. And now as we kind of press play and go forward, we'll see this ball of energy as it expands and starts to cool off. We're going to see some of those pockets as it starts to expand. It's not a uniform expansion. Some areas are going to be more densely packed with this hydrogen gas. Other areas of expansion are going to be less densely packed with gas. This is a picture of that expansion, right? And the little red pockets are going to be pockets of gas. I wish there was a periodic table of elements in here, because what we will see, the very first element that forms as we cross into this line is hydrogen. It's the most simple element in the periodic table. So you had vast clouds of hydrogen as the first elements that show up. And these large clouds of hydrogen, as they expand, again, are not expanding uniformly. There are some pockets of dense hydrogen. And what we see is those little dense pockets of hydrogen start to collapse under their own gravity and rotate. Just like we were kind of seeing hurricanes form. These large clouds of hydrogen are going to cluster together and rotate and form the first generations of galaxies. Here's our Milky Way Galaxy. What's interesting is they have recently found out that about half of the stars in our Milky Way Galaxy come from a previous galaxy, that our Milky Way has already participated in one of these galactic merger events. Some of the stars in our galaxy are like 12 billion years old. Our star is 4.6 billion years old. Our star, our sun, is part of a second or third generation of stars in which, as we're about to see, the very first generation of stars didn't have any planets around them. Stars had to live their lives and create all of the elements in the periodic table. And as they explode, they seed interstellar space with all of their elements that they have created. And the second and third generation of stars that form pull in these dust clouds that end up, the dust itself forms into planets and us. Anyway, here's a picture of our Milky Way Galaxy. We live out in the suburbs, about 2/3 of the way out from the galactic center. And the Earth actually goes, it's on some type of a cycle about every 20,000 years that it dips below and above our galactic belt. And it's kind of thought that we are, when we are in times in the middle of that galactic belt, we are subject to greater chance of meteor impact. But anyway, it's interesting to think about these long cycles. And this is not the Milky Way Galaxy, but it is a spiral galaxy that is thought to be what our Milky Way Galaxy would look like if we could see it from a different angle. Obviously, we're part of the galaxy, so we can't see it from an angle like this. We exist, 2/3 out of the way from the center, out on one of these bands of dust around one particular star that we call the sun. And when we look back to the center of our galaxy, we can't really see that bright spot because there are all of the little bands of dust and planets, things that don't give off light, that block our view of the bright supermassive black hole that's at the center of our galaxy. If I can just jump ahead to this picture right here. This is what we see when we look up at the night sky, and we can see the Milky Way, right? You can kind of see that supermassive black hole, that bright galactic center, but it's blocked out by these bands of dust and planets, things that don't give off light. So that's kind of wild, but let's go back to this picture where we are at. I was just about to talk about on a smaller scale, like this was a giant cloud of hydrogen that condensed, and the center of this cloud of hydrogen formed a supermassive black hole that's like the drain at the bottom of your tub that pulls all of the stuff in. So we've kind of got all that the stuff pulled in around this supermassive black hole. On a smaller scale, there's smaller pockets of hydrogen that are going to form stars out here. And again, not that we have to get into the astronomy class. If it's a large pocket of hydrogen, it's going to form a large, bright star that is not going to live very long. And when it collapses, it could form into a black hole. Obviously not the scale of a black hole that you would find in the middle of a galaxy, these supermassive black holes, but much smaller black holes, stellar black holes that are out here. Smaller stars are not going to burn as hot, so they live longer. Again, that's irrelevant. But what we need to know about stellar evolution, like this is a picture of what's happening in the life of a star. Like I said, what a star is just a pocket of hydrogen that starts to collapse under its own gravity. And what we know about how gravity works and compressing things, right? As volume decreases, the temperature and the pressure increase. Pay attention to the blue lines real quick, because that's gravity trying to pull this cloud of hydrogen more and more tightly in. And as it does so, this ball of hydrogen starts to get hotter and hotter and hotter. And something happens right in the very center of that core of hydrogen. That's the hottest place in that core of hydrogen. And when hydrogen hits a certain temperature, it fuses into the next element in the periodic table, helium. So a star starts out its life with more hydrogen than helium. And as that core of helium starts to grow and swell, you can tell this is one of the ways that they can gauge how long a star has been burning and tell how much longer it has left to burn by determining the ratio of hydrogen to helium. It's interesting that when hydrogen fuses into helium, this is a fission reaction that releases a tremendous amount of energy. So as long as there's hydrogen to fuse into helium, you can see there's this dynamic thing that's happening in the life cycle of stars. They're on the fence, right? Gravity is constantly trying to squeeze them in and ramp up the temperature. And as long as hydrogen is fusing into helium, the red lines are showing us that this thing is a nuclear explosion trying to explode. But what's preventing it from really exploding is gravity still trying to hold it in. So a star kind of lives its life between nuclear fission trying to explode the whole thing and gravity kind of holding that explosion in for just a little bit. What happens as a star starts to age, right? That core of helium starts to swell. And in the middle of that core of helium, that's where helium is the hottest and moving around the fastest. You'll see that inside that core of helium, the next element in the periodic table is going to form in the center of that core of helium. And then as that core starts to swell and become even hotter, these older stars end up being kind of like an onion with multiple layers. And the deeper we go into the onion, the heavier elements in the periodic table we make. Different size stars can have more layers than others, right? So small stars aren't going to make as many of these elements as larger stars. That's why things like gold and platinum are considered precious metals, because not all stars are going to make those. Again, when a star lives its life, it creates a bunch of these elements in the periodic table. Depending on the size of the star, that determines how many it's going to make. But once it runs out of hydrogen to fuse into helium, there's nothing left. That fission reaction that has been keeping gravity from imploding this whole thing, that fission reaction runs out and there's nothing left to hold gravity off. So gravity is going to implode this star. So these old stars, they end up exploding like this. And what they're seeding interstellar space with is the elements that they just created. Here's another picture of that dust and gas that is coming from a region of stellar explosions. I skipped over this slide for just a second, and this is evidence of spectroscopy. If you're interested in astronomy or analyzing the light from distant stars, if you want to know, how do they know that our star, for example, is 4.6 billion years old? How do they know it's got about 4 billion years left of fuel to burn before it starts to do its explosion? They can analyze the light coming from our star, as well as any of the other stars out in the solar system. What's crazy is that if we were to turn the lights on in here, and if we could somehow capture a little bit of the light coming from one of these tubes and pass it through a prism, it would cast a rainbow that would not have any of these noticeable bands in it. It would be just a smooth rainbow. But that's not what you get when you analyze light coming from a star or our sun, any of those light sources. It's crazy that when you split that light through a prism and look at it, some of the colors of the spectrum are missing. And it is they have now figured out that each one of these is like a barcode that you would get on a product in a supermarket that tells you something about, I'm sure this has a barcode on it. Yep, if I scan that, it would tell me dry erase wipes or something like that. And these barcodes basically that you see you can analyze those, and that tells you what elements are present in that light source. And you can actually tell by analyzing this light how much hydrogen to helium there is present. And you can tell how long a star has been burning and how long it has left to burn. Again, spectroscopy. So anyway, about our night sky. Where was I at? I was showing this picture because I wanted to get into just solar system formation, which is going to be out here on one of these bands of dust and gas. The second generation of stars, like I said, that form are going to be pulling in this dust and debris from a previous generation of stars. And this third generation of stars now has dust around it that condenses into planets. We don't have to get into all of the planetary things that need to go right for a planet to have life on it. What we will at least say at this level is that for life to exist as we know it, we need to find a planet that's in this Goldilocks zone, this region of the solar system where water can exist in a liquid state. Here's a really big star, so this is going to burn really bright and it's not going to last as long. You don't want to be as close to this star, so the habitable range is a little bit further away. Obviously too close and water is just going to be vapor. Too far away and water is going to be locked up as ice. So we need to be in this tolerable range. You can see as the star gets smaller, it doesn't burn as bright, so that range of this habitable zone becomes smaller. I will say this, even though that range of the habitable zone is smaller there, these stars live way longer than the bright stars. So there's a larger habitable zone here, but these planets are not going to be able to, they're not going to last as long before this star explodes. So when we're thinking about trying to find life out there in the universe, like that new James Webb Space Telescope just got to its spot. And I'm jealous that I'm not going to be around as long as everybody else in here to see what kind of things that thing comes up with. But, when we're looking we will see that life, the chemistry for creating life, might not be that rare out there in the universe. But as far as intelligent life forming, that might be way more rare. And for intelligent life, life to be around long enough that develops language and iPhones and the internet and D2L and all that type of stuff is going to require time. And so that's why if we're looking for things like intelligent life, they're trying to find habitable zones around smaller stars, because this is just going to be a system that is around so much longer, and it gives a longer time span for intelligent life to show up. We will see this on Wednesday, so I won't say too much about this. Other than introducing the fact that this is the Miller-Yuri experiment. It was first done back in the 1950s, and they found that, with this simple contraption that had boiled water that simulated some type of atmospheric gases, there was an electrical spark that simulated electrical strikes. This water was kind of allowed to circulate in the closed tubes. There was a little bit of methane gas, some simple elements from the periodic table that come from the death of stars, added to this water, and within a couple of weeks, the water started to become this murky brown color. When it was analyzed, they were finding in this water the amino acids that were starting to spontaneously be formed. It was a little interesting that the amino acids that they were finding in this Miller-Urey experiment were equal numbered mirror image molecules, right? If we put our 1406 hat on for a second, we said when we were looking at molecules, there were these mirror image versions of molecules. We called those enantiomers. And they didn't behave the same way in our body. Like all of, when we were talking about glucose, there are equal an artificial sugar that is artificially made. It is made in equal parts, left-handed and right-handed versions of this glucose molecule. And your body can only digest the left-handed version of that glucose. And the other 50% goes through your body without you being able to do anything with it. That's why when they were marketing whatever it was, natural cane sugar or something like that in Dr. Pepper or Coke, whatever it was, that cane sugar, that's made by plants. And so that's only making the left-handed version of the glucose molecule that your body can consume. They found amino acids in here that were equal numbers of left and right-handed parts, meaning that these were amino acids that were made through kind of an artificial process. It's, again, like the sugar that's made. I feel like we talk a little bit more about this stuff on Wednesday, but to kind of get into a little bit of a side note about this as well, there was a meteor that fell to the Earth. I forget exactly the year, not too long ago, but there were amino acids on the meteor as well. And what was unique about the amino acids there, they were also equal number left and right-handed versions of those amino acids, kind of indicating that they might have formed in one of these processes that maybe just before life started to evolve. And, you know, I have to get into a little bit of discussion about life as we know it, right? When we start to get into the formation of living organisms, it's crazy to think that all of the life that we have known so far, if you look at it, it's only using left-handed versions of these molecules, of these enantiomer molecules. It's interesting to think that on another planet, on another solar system, there's nothing against the laws of physics that says there might be forms of life that use the other version, the right-handed versions of those molecules. I'm getting off into an even further side note here, but let's do a little thought experiment that if we were to go back in time to when, you know, there used to just be nails when we were building stuff. People had a hammer and a nail, and then at some point the screw was invented, right? Where you've got these threads and you can screw this threaded nail into something and it holds a tighter connection. Originally, when screws were invented, there were left-handed threaded screws and right-handed threaded screws. So when you were to grab a screw at random, you didn't know if it was the type of screw that you had to go clockwise to get it to go into the wall or counterclockwise to get it to go out of the wall. There were left-handed and right-handed threaded screws. But that was in the past. One of those branches of screws has gone extinct while the other one has survived. We'll see an analogy with a lot of species this way. So if we were to go into Lowe's or Home Depot right now and walk down any of those aisles and grab a random screw, I bet it's going to be one of those screws that's threaded in such a way that we have to go clockwise, spin it clockwise to get it to go into the wall, and counterclockwise to come out of the wall. Right? There's nothing against the laws of physics that says we can't build a screw the opposite way. It's just that all of the screws that we use now are that right-handed threaded screw. That's an evidence of common ancestry of all the screws that we have at Home Depot right now. Just like when we look at evidence of common ancestry of living organisms, that suggests a common ancestry of all of us, that we all use the left-handed version of these molecules, when out there in nature it seems like there are equal numbers of left and right-handed versions of these molecules, in this case amino acids. Peeling myself away from that. To look at this is also another thing that's kind of interesting. This is a picture that I think I took this last winter, and this is in camera, and this is at night. All you have to do is point a camera towards the north part of the sky, and it's going to catch some kind of picture like this. I think this was like a 20-minute exposure or something like that. And what I'm trying to show here is, this is kind of interesting, again, thinking about Earth science and how the stars move around the sky at night. I think we are all, you know, like me, I feel like we all grew up in an area where we are fortunate enough to be able to walk out at night and see a pretty good view of the night sky and all the stars and stuff like that. And I was always very curious as to, you know, again, I'm from Cameron. I didn't travel up to the North Pole or to the equator ever in my life. So it's kind of weird to just think about how things look to us and where we are at. For example, when you see a picture like this, if we go from the horizon line, which is, we can see a little bit of a cabin right there, and if we draw a line from this horizon line up to where we see that North Star, this is an indication of the latitude that you are on the globe. Right? We are right now at about 45 degrees latitude, so that North Star is about 45 degrees up. right? It's about halfway up between the horizon and directly above our heads. If we were to go up to the North Pole, if we could just have a little field trip where we all go up to the very North Pole, what we would see, that little North Star, it would be directly over our head, right? And all of the stars, this whole spinning, these stars would be going around us like this. So that's why you see, if you're at the North Pole, sometimes the sun barely comes up over the horizon and then dips down below the horizon, and it barely comes up in the sky at all. Whereas if we were to all go to the equator, that North Star would go right down to the horizon, and all we would see would be the stars going across, vertically across the sky. So this is a good indication of what latitude you are on the globe. Right? And again, not that that's on the exam, but it's a good thing to know something about Earth science. Right? I think flat earthers would have a hard time explaining how is it that when you go to different latitudes you see different orientations of the stars like this. The other thing that we want to point out is that right now, in this 20-minute exposure, that North Star, if you look closely, it's not exactly it's not perfectly north, right? If I let this thing go for like a 2-hour exposure, that North Star would make a tiny little loop, just a small little circle right there. Even more interesting, if we could continue to take this picture, like in the next 2,000 years, and then 4,000 years, and then 6,000 years, what we would see is that circle right there would start to become larger and larger. The Earth is spinning right now, kind of like a top spins, and it would be, again, I'll preface this a couple of different ways. Like if you see a top spin, and eventually as the top starts to lose some speed, it starts to wobble back and forth. Right? That wobble that the top does as it starts to lose speed is what we call precession, that wobbling effect. And the Earth is doing that too. The Earth is spinning and it has this wobbling effect, not because it's losing speed like a top does, but because it got slammed by the moon at some point in the past. So that put Earth off on this little bit of a tilt, right? So it has this precession or this wobble to it. And it takes about 40,000 years for this cycle, for one of these wobbles to go from one extreme to the next. It is what causes the North Star to change over this 40,000 year cycle. Right now, we're somewhere close to the path of true north as the Earth spins, pointing somewhere close to Polaris. But again, in about 5,000 years from now, that North Star, if we were to take that same picture, the star that's right in the middle and not moving would be Thuban. And then, a full 20,000 years from now, that star that we would recognize as the North Star would be closer to Vega. And then again, it's eventually going to make its way all the way back around. These are called the Milankovitch Cycles. This was a Russian scientist that figured this out. This is, again, not on the exam, but if you're interested in precession, wobble, Milankovitch Cycles, this is all here. This is also the thing that debunks, like if you wanted to make and I hate to burst any bubbles here, but if you wanted any kind of distinction between astronomy and astrology, right? Astrology is looking at horoscopes and values and things like that, and using the path that the sun takes through the stars and different constellations to figure out something about, who you are, your behavior. That astrology, all of that stuff was invented like 2,500 years ago. Back when, if I can go back to this picture here, like we are currently reading those horoscopes as if they are current, but they are now about almost 3,000 years old. So if you factor precession into the horoscopes, it would mean that the signs that like I'm born in December 31st, if you believe in that stuff, I would be a Capricorn. However, if you take into account that that's now almost 3,000 years old, so the adjustment is about 2 signs off what it currently is. So I've been living my whole life thinking I'm a Capricorn, but really, when that was invented, I now changed. Precession has wobbled it so far off that it's 2 signs off of what it originally was when it was invented back 3,000 years ago. So turns out I'm not a Capricorn if I was to really go off of what that, when that was invented. But again, That is not true science. So there is a difference between astrology and all of that stuff and astronomy, which seeks to ask these questions and get some answers out of them. More stuff on astronomy, I guess. Right before we switch gears into climatology and geology real quick, I'll say something about this magnetosphere. If you haven't seen anything about this before, this is a magnetic force field that is generated by the fact that the core of our Earth is not completely solid. If I can jump to this picture real quick. Here's a picture of the fact that our core of our Earth is, the heavier elements are going to sink towards the center of the Earth, and they're hot, they're molten, they're not completely solid. These metals kind of slip past one another, and they create this static electricity. It is not unlike, in the wintertime, if you scuff your feet while you're walking across the carpet, building up a lot of that static electricity, and then touch a doorknob or touch your friend or something like that, there'll be a little bit of that electric current that is formed. That's what is happening down here in this core that generates this magnetic sphere. So there's our magnetosphere. It's a good thing that we have it, because what that magnetic force field does is it prevents this radiation, this solar wind that's coming from the sun, from blowing away our atmosphere. You can see the weak points in the magnetosphere are at the South Pole and at the North Pole. So if you go to the South Pole or the North Pole, anywhere close to the polar regions, you can actually see some of the atmospheric gases escape this magnetosphere and be blown away by the solar winds. That's what the auroras are for, these northern lights. That's atmospheric gases that have made their way up through the magnetosphere, and that solar wind is blowing them off, losing some atmosphere there. I also remember years ago watching a documentary on Mars, well before they sent any probes there, and they found out that Mars is a lot smaller than Earth is, so it cooled off more rapidly than Earth did. At one point, it was thought that Mars, when its core was still molten, had not yet solidified yet, it had its own magnetosphere, it had its own atmosphere, it had its own weather, it had its own water. But whenever it cooled off to a certain point, the core became solid. It lost this magnetosphere, and the solar winds blew all of the atmosphere away. So now when we look at it, it looks like a barren desert, and the only water that they're finding is like ice locked away underground at the polar regions. Currently, like Earth, luckily we're still in that zone where our core is still molten and we still have this magnetosphere, but our core is cooling off, and this magnetosphere is actually getting weaker as we speak. It's interesting that the north and south poles have actually flipped back and forth with some regularity about every 200,000 years. North and south flip in terms of how a compass works, and we're actually overdue for the last flip. So again, interesting stuff about magnetosphere if you are into that. What else did I want to say? I was just talking about the atmosphere, how we need this magnetosphere to hold in the atmosphere. And that's where this picture comes in. This was taken from the International Space Station. It shows the surface of the Earth, and then you can see the upper limits to the atmosphere. It's a relatively thin layer. It's only about 36,000 feet up until you reach the ceiling, the limit of the atmosphere. So all of the weather clouds that we see, those thunderheads that go way up in the sky, they only go up to about 36,000 feet, and then they can't go any higher. They hit this ceiling, and then they expand out. A couple of things. I might have said before that if we were holding an apple in your hand, that if that apple represented the size of the Earth, that the skin of that apple would be relatively as thick as the atmosphere is on our Earth. I remember a conversation I had with one of my buddy's dads, and he was saying, I just don't see how, the emissions that are coming out of my tailpipe have, they go up in the air and then they just, they diffuse. I don't see what that has to do with affecting any of the atmosphere. It's such a large atmosphere, But when you see it from this angle, you see how thin it is over the surface of the Earth. And I invited him, even though don't ever really do this, so hopefully this is caught, but I will say don't ever really do this, but you can do the thought experiment of if you were to take just your one vehicle and drive it into a garage, right, and close that garage door and roll the windows down and leave that car running, it wouldn't take very long before that one car affected the quality of air in the garage, right? It would be not in a beneficial way. So with all the cars that we have on the road all over the globe, it is something that can accumulate in the atmosphere and have some effects. Anyway, not that we have to get into climate science, but this is what we will say about climate science. We need to know something about weather patterns broadly. And I should qualify that everything that we're about to say here goes for the northern hemisphere, and it would be the opposite in the southern hemisphere. But we see a couple of things on this slide. First off, what we're looking at down here, these vertical columns of air that are either moving down to the surface or vertical columns of air that are moving aloft. Remember that there's only so far up that these columns can move up. There's about 36,000 feet until they hit a ceiling. And then at one point, once these vertical columns of air hit that ceiling, they can't go up anymore, so they diverge away from one another. If there's divergence aloft in a rising air column, this is what is associated with low pressure, rising air columns. These are always associated with rainy days. So right now we are in a low pressure zone versus days like if you hear on the weather that we have a high pressure zone that has moved in over Texas and is going to provide nice weather for the next 3 or 4 days. High pressure zones, this is just a case where you have a vertical column of air that is moving towards the surface. And the reason it moves towards the surface is you've got converging air masses that converge up at the roof, the ceiling of the atmosphere. Again, they can't go any further up, so they're pushed downward. There's a recurring theme here, right, with physics. As anything is compressed, right, as we have this pressure, this current of moving air that's moving towards the surface, this air is going to be heated up. And obviously it can't go down into the surface, into the ground level. So once this downward moving column of air hits the surface, it diverges at the surface. Vertical moving columns of air are going to do the opposite, right? As they move up, they are expanding and they're cooling off. So the analogy that I used was that bathroom analogy of, like when I get out of the shower, sometimes I have to shave my face. And if I let the shower run too long and it gets, the water from the hot shower gets into the air, if the bathroom is too cold and that air doesn't hold on to the water, then that water ends up on the mirror and it causes my mirror to be all foggy. And I have to wipe that off before I can see myself to shave. But here's the tip. One thing that you can do to prevent that mirror from fogging up is to put a heater in, a little space heater or something like that into the bathroom. I should always say don't plug that space heater up to an extension cord. Those should go directly into the wall. But anyway, space heaters, right, if you were to heat the air of the room up, warm air is going to hold on to more moisture, okay? Meaning that if I heat that air up in the bathroom, when I get out of the shower, even though there's a bunch of water vapor in the air, that warm air can hold on to it and prevent it from ending up on the mirror. Okay, let's see that here. Remember, hot air, these high pressure zones, this is going to be air that is being compressed towards the surface. As this air heats up, it's basically baking out the land that is underneath there, absorbing all of the moisture, because again, hot air can absorb more moisture. If we think about what happens in low pressure zones, it's the opposite. We've got a vertical moving column of air that expands and cools off. And like I just said, cold air, it can't hold as much moisture. So when we have cooling air masses, they lose their water. So we had a little bit of rain this morning, and that tells us that we're in one of these low pressure zones where there's a vertical column of air that's moving up, becoming less dense and dropping its water. The thing that we're seeing up here at the top, this is just what happens. This is due to the Coriolis Effect, the fact that the Earth is spinning. Again, probably more than we will know, but you've got this vertical column of air that is either moving down or moving up. If we've got a downward column of air, one of these high pressure zones, as this thing spins in the northern hemisphere, it's going to spin in a clockwise fashion. So if you look at the weather, whenever they're showing weather on the news, high pressure zones always spin in a clockwise fashion. Low pressure zones are always going to spin in a counterclockwise fashion. So when we see like images of hurricanes that hit New Orleans or hit any of the Gulf Coast, they're always spinning in this counterclockwise fashion. Anyway, just to give you a little bit of idea of why we have these air currents in the first place, like if we think what causes wind, why do we have wind in the first place? What is the purpose of wind? What wind is trying to do is it is an attempt to evenly distribute temperature across the surface of the globe. We've got two horizontal yellow lines here, okay, and they're actually the same width, so that you can see, we can allow this yellow band to represent UV rays that come from the sun. And we can see these UV rays that make contact at the equator, more of a direct hit on the Earth. These are concentrated UV rays. They spread out over, we'll say, that much surface of the Earth. But we can see that same quantity of UV rays that happens to hit closer towards the polar regions. Again, same amount of UV rays, but you can see how it's spread out over twice the amount of surface area. So these are much more diluted UV rays than would be hitting right there on the equator. These more intense UV rays mean there's a lot more heat here, and what the wind is trying to do is trying to evenly distribute that heat from the equator towards the poles. And how it does that, how it distributes that heat, is with a few different circular patterns that we're going to see. These circular patterns are going to mirror each other in the southern hemisphere and in the northern hemisphere. We'll talk about the ones here in the northern hemisphere. We'll see this in the next slide. This first cell we're going to call a Hadley cell. It goes from the equator to about 30 degrees latitude. This next one, just to jump to that detailed slide, there's a lot going on here, right? But I was just talking about this Hadley cell. That's the one right next to the equator. There is a Hadley cell close to the equator in the southern hemisphere and in the northern hemisphere. So those flank the equator. Then that middle cell in between the polar cell and the Hadley cell, that one in the middle is called a Ferrule cell. Same naming for the southern hemisphere as for the northern hemisphere. There's that Ferrule cell. And look at how obviously where the two Hadley cells meet, that's right here on the equator. You can see how the circulating current goes between those Hadley cells. Right there on the equator, you have two air currents that meet at the surface, right? And they can't go down into the ground. The only place they can go is vertically up. So like we were just seeing in the previous slide, a vertical column of air that moves up is going to expand. It's going to lose its heat. When it cools off, it's going to drop its moisture. So we see these bands of rainfall in between two Hadley cells, right? If you ever wondered why is there so much rain at the equator, it's not just because there's sun hitting, it's because we have this interaction between two Hadley cells where there's a vertical column of air that cools off and drops its moisture. Okay, then let's look at this interaction between the Ferrule cell and the Hadley cell. If you look what's going on here, you've got two air masses that converge at the ceiling, up at the roof of the atmosphere. So convergement aloft means that these two air masses, once they meet way up here in the atmosphere, they can't go any further out, right? They then can only go down towards the surface. And this is a high pressure zone, right at about 30 degrees latitude in the southern hemisphere and in the northern hemisphere up there. You can see how we have these high pressure zones that are built in. What we know about high pressure zones is that air is warming up. Warm air is going to hold on to more moisture. So you see a baking out of the land at about 30 degrees latitude, south of the equator and north of the equator. So the world's deserts are all at about 30 degrees latitude. And again, that's due to this interaction between the Ferrule cell and the Hadley cell. If we go all the way to the poles, there is a polar cell. So it's easy to remember. There's a polar cell at the North Pole and a polar cell at the South Pole. Between the polar cell and the Ferrule cell, whether it's the southern hemisphere or the northern hemisphere, you can see that once again there is going to be converging air flow at the surface. So the only place that air could go would be up, and as air goes up, it cools off and drops its rain. So at about 60 degrees latitude in the northern hemisphere, we're going to see a bunch of rainfall. And you also see a bunch of rainfall at about 60 degrees latitude down in the southern hemisphere. If I can just jump to this slide real quick. Again, we're trying to work our way out to ecosystems and biomes, right? And I'm trying to talk about the forces that have created certain ecosystems and certain biomes. Like, why do we find rainforest always along the equator, right? Why do we find deserts at about 30 degrees latitude in the southern hemisphere and in the northern hemisphere? Some of it has to do with geology and how those continents are moving around, but a lot of it has to do with the climatology, those circulating currents of air up in the atmosphere that are baking out certain regions, right? or allowing for a bunch of rainfall. Look at how when we get all the way up to, so 30 degrees latitude, there's where all the deserts are in the northern hemisphere. But once we get up to about 60 degrees latitude, there is once again another forest where there's enough rainfall to support large trees. This is all the coniferous forest up here. But down here in the southern hemisphere, there's not a bunch of forest, and that's not because there's not enough rainfall to support it, but it's the luck of geology, or the bad luck of geology. There just so happens to be not a lot of land mass in the southern hemisphere at about 60 degrees latitude. So there's no places for the plants to grow. But we would assume that if there is land down there in the southern hemisphere, that you would have a bunch of vegetation there because there's enough rainfall to support it. Right? I feel like we're pretty zoomed out. We've gone through astronomy and we've gone through a little bit of climatology, so let me just say briefly something about geology, and that is the fact that it's also not been known since the 1960s, maybe, I forget, 62, 63, one of those years, following World War II, when submarines were not being used to plot and bomb and do war things. Scientists got into these submarines and went down and mapped the ocean floor. And it wasn't until then that they actually found something that looks like this. I'll just go to this picture. It shows that there are these little tectonic plates that all fit together like a jigsaw puzzle. And when you, like I grew up again in Cameron where there's not a lot of volcanoes or earthquakes or things like that. It's not a geologically active region. And when you think, I would always wonder, why do mountains form where they are? And why are some areas geologically active with lots of volcanoes and earthquakes and other areas aren't? And it has to do with where these plates are bumping into one another. It's also, again, since the 1950s, they've put little markers, little geo-trackers on all the different surfaces on the different continents. And they've tracked them with satellites to see how fast, in what direction are these continents moving around. Most of them move at about the pace that our fingernails grow, but other ones like this Indonesia plate ended up moving more rapidly. So some of them have a little fast track. And when they slam into one another, that's what leads to a lot of these earthquakes and geologic activities. In fact, the thing that we just saw last week on the news, that the Tonga Explosion, did anybody see those things? Wild explosion. This is probably the worst picture to show that, but that was just above. Here is New Zealand, and we can see how geologically active this area is between these two plates. The picture gets cut off over here, but you can see that little hot spot of geologic activity pop back in the field of view, barely over here, and it's in this little hot spot, kind of east of Australia and north of New Zealand that volcanic eruption took place. So always at these little plate boundary zones. I'm going to go back to this, just kind of showing that we have also underneath the surface of our crust these convection currents. And in some places of these convection currents, we have these pockets of hot magma that are welling up to the surface. This is where two of these convection currents have met, kind of pulling heat to the surface. This, again, maybe to simplify what we're looking at here, the mantle works not too much unlike a lava lamp works, in the sense that, when things get down here close to the core, it's hotter down here, so they heat up and they expand. And as they expand, they're less dense. So things, as they become less dense, they start to float up to the surface. But when they float up to the surface, they lose their heat. They become cool and more dense. And as they become cool and dense, they sink back towards the center of the earth. And as they sink down, they heat up, they expand, they become less dense, and they float back to the top. Just like a lava lamp works. That stuff drops down to near the light bulb, and that light bulb heats the goo up, and the goo expands and floats to the top until it cools off and becomes dense and drops back down again. The whole point, we've got some areas where there is this upwelling. It leads to this ridge push where there's diverging plates. So sometimes in geology we see these diverging plates. It's currently what is pushing North America and Europe further apart. Same with South America and Africa are getting pushed further apart. At some point in the past they were closer together. Not only do you have this divergence, in other places you have plates that are being pulled together, and this is what allows for the uplift, for continents to form, mountain ranges. All the geologic activity like volcanoes are due to plates that are slamming together. Places like the Atlantic Ocean are examples where there is a ridge push and sea floor spreading. So the youngest sea floor is laid down right in the middle of that seam, and you can get progressively older. In fact, I'd mentioned earlier about how the magnetic sphere flips north and south about every 2,000 years. They get, this is additional information, but this mid-ocean ridge, what you have is you have magma that comes up to the surface and cools off. And if you are a fan of geology, you know that you can date rocks that cool from magma. We can't go get a sedimentary rock and date that because it's fragments of a bunch of older rocks. But rock that is igneous rock, that cools from magma, you can date that rock to see when it formed. Interestingly enough, also, any of the iron fragments in this rock that solidifies from magma, those iron fragments line up with the magnetic pole. And you also get, again, the closer you are to this ridge, the more recent that new rock has formed, and the further out you go, the older that rock has formed. So you can get a good snapshot of looking at how those iron fragments in rocks align. You can go back, it's every 200,000 years that these things flip. You can go back millions of years to see how often the north and south poles have flipped, and that's how they can tell that we're due for a flip now. I didn't bring a picture of that, but you can look up magnetic pole reversals and igneous rock to tell the history of that. Anyway, way off in geology there. Let's try and come back a little bit closer to Texas geology now that we've kind of set up a little bit about these biomes. And again, taking the big picture approach, we're thinking about animals that are riding around on these continents. We have to know something about that the continents move around, and as these continents move around, they are inadvertently moving into areas that are going to become desert-like just due to the climate science that's there. And if they move across the equatorial regions or even 60 degrees latitude region, they're going to move into some of these rainforest regions. The rainforest could be hot like it is at the equator, or the rainforest could be cool like it is up there at 60 degrees latitude. There's a bunch of different biomes, basically. We don't have to know all the different types of biomes. They're all characterized, obviously, by different climatic patterns and different communities of organisms that live there. Here is a list of some basic different biomes. Again, we won't have to remember each of these, but it gives you an idea that there are things like Arctic tundra that is dry but extremely cold, contrasted with things like a desert around 30 degrees latitude, which also are very dry, but they're very warm. You've got everything in between, like those coniferous forests that are mostly pine trees. They don't lose their leaves, versus the deciduous forests, which are trees that lose their leaves in the fall. Some areas don't receive enough rainfall for trees to grow at all, so they're grasslands. Savannas are somewhat moderate with enough rain for grass and some shrubs. So there's a mix of different biomes. If it's a textbook that takes a broad approach on biomes, you might see about 8 different ones. There are other versions of textbooks that get a little more detailed. So you can see this is a much more detailed map of different biomes in the northern and southern hemisphere, or North and South America, I should say. And this is expanded over there for Africa, Europe, and Australia. Again, we don't have to know all the different ecoregions all over the globe, but what we need to know basically is that there is a connection between diversity of habitat and diversity of species. In fact, there are certain biomes that are more diverse than others. These biomes that are extremely diverse in terms of the number of species that they house, these are called hotspots, and there is kind of additional significance that's put on trying to save these areas, because it's just a handful of areas that house over half of the world's diversity. Let's look at that. Right, if we're thinking about distribution of organisms, this brings us over to our chart. Last semester, we stopped at the organism level, and this semester we're going to blow past that into populations and communities and ecosystems. Remember our population dynamics. We ourselves in here in our 1407 class are a good example of a population where a group of individuals in the same area at the same time. We can easily count population size in here and see how it changes throughout the semester just by counting the number of individuals in our population. We'll see as we get out into the world and collect data, we'll see that population density can vary. It can also be interesting because it changes the way populations behave if they are extremely confined or in a dense area versus spread out and less dense. There's a way that we can map that called population distribution. The ways that we can see distribution of populations are typically in a clumped pattern or uniform, nearly uniform. Here's a picture of what that looks like. Clumped populations, that would be like if we had, if y'all were sitting a little bit more closely together here, and then we had a clump of people over here, and then more a clump of people in the back. We're not clumped in here. It doesn't look like we are uniform either. That would be everybody's kind of spaced out where there's equal distance between one another. Looks like we're more randomly distributed in here. That's probably to be expected. But when we think about biodiversity, it's not just the number of species, it's how many individuals of that species are present. And we know there's a strong correlation between number of species, the health of those species, and the number of habitats that are available. And I think I tried to say something when we went through that lab last semester, is that we don't know what climatic conditions are going to hold in the future. So one of the best safeguards that communities can have is to protect this biodiversity, to have as much diverse forms in the community as possible. So, in case the climate shifts one way, well, we've got something that can handle that. We'll be okay. Right? And if it shifts a totally other way, if we're extremely diverse, hopefully we have something that can handle that. We lose our biodiversity, we could become vulnerable to extinction. Here's an example of biodiversity, and it's something I may have mentioned before. If not, it's kind of a famous example of what happens when you mess up species diversity in an ecosystem. And back when people were trying to move west and colonize California, they settled in Yellowstone National Park because it's gorgeous. But the downside was that there was a lot of wolves that could eat your baby while you're washing clothes down by the creek, right? So everybody was nervous about that. So they thought, let's kill off all of these wolves. They're predators. They weren't as worried about the elk because the elk's not going to come steal their baby when they're washing clothes by the creek. But the wolves were. So they went on this hunting of wolf. What am I trying to say? That was their mission, I guess, to hunt all of these wolves down. And they were successful in doing so. By the 1930s, all of the wolves in Yellowstone were gone. So it was a big success at first. But then the people started to realize very quickly that they've messed something up. The biodiversity is out of whack. It looks something like, there's a lot going on in this slide. I'll first want you just to look over here at the left-hand side of the slide. And what we can see here is what the ecosystem of Yellowstone looked like after they decimated the wolf population. Elk that were the main food for the wolf population, elk no longer had a predator to fear, and their populations exploded. So we have way too many elk just kind of hanging out down here at the creek, eating up all the vegetation. So the plants really got decimated. There's a lot of birds that like to make their nest at the mid-story of trees, and those birds didn't have any homes to build nests because all the trees were gone. Beavers even like to use those smaller trees to build dams, and then that leads to little ponds and pools of water that build up, and you can get fish in those pools of water, and amphibians and raccoons that like to come eat those fish, and all of these things. But you don't have that with all the trees that are gone. Instead, you can see coyotes also started to increase in number. Coyotes are not as big as wolves, so coyotes are not going to take down an elk. So elk population are not scared of the coyote. Instead, coyotes are going to be taking smaller mammals like field mice and rabbits and raccoons. So we are losing a lot of the field mice, rabbits, raccoons, a lot of the smaller mammals, and the amphibians are being taken out by this coyote. we're losing a lot of the species diversity. There's a couple of species that are doing well. The coyote and the elk like it. But again, we're losing a large number of species. What was done in this was 1995. So not too long ago, the gray wolf was reintroduced back to Yellowstone, and it took only about 10 years. And what happened is the wolf populations quickly reduced the number of elk. So the elk population was back down to its normal number. That allowed the vegetation to rebound, and you get more birds that have now built nests in trees. You get beavers that can now build dams and back up little ponds of water. So you get more fish, more amphibians, more snakes. Just a much healthier ecosystem in terms of species diversity. This is what we would want to deal with any type of climatic changes going forward. This ecosystem is on the brink of extinction, right? It's vulnerable. Okay, so we've seen something about ecosystems. We talk about how they formed. I know I'm getting close to the end of this PowerPoint. I appreciate everybody's patience. But I just wanted to say something about Texas geology and how it is that we have the ecoregions or the ecosystems that we have here in Texas. I tried to overlay these two pictures. Next to the ecoregions of Texas, you can see the Texas geology. And I know this is kind of small. It's hard to see what any of those words mean. But you can see a geologic time scale that we're going to see in our lecture next time. And this shows us that the youngest sediment, the youngest ground that we find in Texas is right here next to the coast. And each of these lines that we see kind of coming down this way, this is an indication that the levels of the ocean have been receding for, I don't know, I would be guessing at exactly how long they have been receding. But it turns out right now, the time that we live at now, they are no longer receding, but they are actually starting to move back the opposite direction. So it's not clear yet, if the oceans were to rise, how much of this land would be covered up. But oceans have fluctuated many times in the past, and it is actually the receding ocean that is responsible for the newest layers of sediment that have been exposed here in Texas geology. So this is the youngest sediment. You can see it right there off the coast. Now, there's something interesting as we get into the middle of Texas here. There's this little area this is called the Balconies Escarpment. An escarpment is basically just a place where the land breaks in half. And that's because, I know I'm just using my hands here to do this, but you can imagine if one of my hands started to get let's say this hand right here started to get a bunch of extra stuff added on top of it. And this hand started to become very heavy. Maybe to even make this a better analogy, well, let me just say it like this. My hands that I'm trying to use right here, this is really Texas, okay? And if we think about the history of Texas real quick, I'll use my slides to do this. Texas is interesting if you think about its history. There used to be a mountain range that moved right through the middle of Texas. This mountain range is about 350 million years old. This is the same chain of mountains that was responsible for uplifting the Appalachian Mountains, these Ouachita Mountains that are through Oklahoma and Arkansas, down through Texas and even out into the Big Bend region. There is a core of the ancient core of one of those mountains in this old mountain range has been exposed through erosion. And you can see the dome of that old core of a mountain if you go to Enchanted Rock, right, and climb to the top of an Enchanted Rock. That rock that you're on top of is 1.1 billion years old. I said we'd be throwing around some random ages, right? The Earth is 4.6 billion years old. The oldest rock we can find in Texas is 1.1 billion years old, and it's that Llano Uplift right there. This is an ancient mountain chain. If you've been to the top of that Llano Uplift, even at the very top of that dome rock, if you look out at the horizon in all directions, you just see the tree line. You're actually down in a hole, even when you're on top of that little dome. Maybe we could take a field trip there. Anyway, the point that I'm trying to make here is that there was a time at about 300 to 350 million years ago where there was a mountain range that went through the middle of Texas. And if we can imagine, this uplift of this mountain range around 350 million years ago, it's what led to, at that time in Texas past, the rivers were flowing west. and they deposited all of their sediment out here in West Texas. This, as we will learn in our geologic time scale, we will refer to that time about 300 million years ago as the Permian era, right? Rivers flowed west out into this area, which is why this is referred to as the Permian Basin, right? All the rivers are flowing out that way. There was also a lot of oxygen in the atmosphere at that time, which is why there's an orange stain to a lot of that soil that's out there. I just threw this picture in there. It's going to be something that we see next time, but it shows this collision between North America and these other European continents. It's what led to that uplift of the Ouachita Mountains, the Appalachian Mountains, those ones that went right through Texas. But since then, right, after this 300 million year old mountain chain came to be, it's been slowly eroding. That's an old mountain chain. And a more recent mountain chain, if I can go back to this, here's that Permian Basin area where all the rivers were draining into. But let me go to this picture real quick. We've now jumped to about 100 million years ago. And at this point, what you can start to see is there's a warm, shallow sea that made its way all the way through the interior part of the United States. And this is what led to the formation of a bunch of limestone rocks. You can find a bunch of fossil deposits in there. But look over here. You can see the Rocky Mountain chain, which is a newer mountain chain than the Appalachian Mountain chains. This is basically on its way up. And it's been rising ever since about 70 million years ago. If we could imagine this mountain chain getting higher and higher into the atmosphere, what it starts to do is it starts to tilt Texas kind of in this direction where the panhandle is higher elevation than everything down here near the Gulf. Right after about 70 million years ago, if we go back in the past before 70 million years, all the rivers in Texas were flowing this direction, at least from the escarpment this direction. But since about 70 million years to the present, all of those rivers have been flowing across Texas into the Gulf of Mexico. So to finally get to that thing I was doing with my hands. For about 70 million years, as rainfall has hit Texas, all of that topsoil, the sediment on the surface, has been stripped away from the west side of Texas and deposited onto the east side of Texas. And over time, what that has led to is that this part of Texas, the west side, has become not as heavy, right? Because we've removed the topsoil, and then at the same time we've deposited that topsoil on the southeast side of Texas. So there became this imbalance, and what happened is the land basically just broke, and that break is the escarpment. That's also why everything over here is got twice as much topsoil as you find over here on the west side. If I can get to this colored map here, this shows us, we are right on the edge of this little escarpment where the little narrow bands, this is all the blackland clay. That's great farmland. When I drive east to Cameron, I'm driving through all of that. So if you were to get into the rivers around there, they would be extremely muddy. You can't see the bottom of them. But if we go west, just on the other side of I-35, we're now into this green patch, the Texas Hill Country. And there's not a lot of topsoil there. It's not great for farmland up there. If you were to get a shovel and try and dig a hole, you don't dig down very far before you start running into that limestone rock. Not the case out here in the Blackland Prairie. We could dig many feet into the ground before we run into rocks. So you've got this natural geology of Texas that has kind of lent itself to these different ecoregions that we will talk about. Maybe with one kind of unique feature there being the enchanted rock right in the middle. Oh, that is the last slide. Okay, so maybe to tie in our broad perspective to stuff that we're going to see next time, I'll end with this slide. We're going to start with Earth history. And we're going to go through different stages of Earth history from its formation all the way to the current date. This stuff that we talk about next time is going to show up on a quiz that will be available on D2L on Wednesday. You'll have a whole week to complete this once it shows up. We're going to put a name and dates to different geologic time periods. And again, I invite people to ask questions like, how do we even know? How do we get the age of the Earth and all kind of things like that? Are there any questions before I close it off? If you think of any between now and next time, feel free to shoot me an email or bring them to class next time. I guess if there are any questions, I'll close it off. But I appreciate your patience.